Hey everyone, now that we are studying slope stability analysis, it is very important that we understand some basic concepts regarding the shear strength of soils, soil mechanics. And so in these videos we are going to do a quick review of some of the most important concepts on how soils react to stress and shear. So why do we care? In order for any slope stability analysis to be useful, we have to have the correct problem correctly formulated, and to do this, in addition to knowing geology and site conditions, we need to understand soil mechanics, and we need to, of course, know the properties of the soil at the site. Their unit weight and their shear strength are the two most important things that we need to understand. And slope stability is actually a really good laboratory for engaging with basic soil mechanics principles. And so let's get started. One of the most important concepts when you're dealing with shear strength of soils, in fact, I would argue maybe the most important thing, is understanding of effective stress. Effective stress at a given depth in the soil is basically the stress applied to the soil particles. Now, the total stress, and we're talking that you can have both vertical and horizontal stress. You can have stress in any direction, actually. But we're typically looking at the, let's do this discussion in terms of the vertical stress. Stress in general is force divided by area, and effective stress is a function of the, as I mentioned, the interparticle stress. Now, what else is there? There's the pore pressure. The pore pressure, the total stress includes both the effective stress and the pore pressure. And so the effective stress, you can think of it as the force carried by these particles that are connected divided by the total area, cross-sectional area we're looking at, where we're considering the stress. And so the total stress is equal to the effective stress. We designate effective stress with sigma bar, or sometimes we do sigma prime with a little apostrophe on it. And the total stress is equal to the effective stress plus the pore pressure, or if you rearrange this a little bit, the effective stress is equal to the total stress minus the pore water pressure. And another really important thing to remember is shear strength is primarily a function of effective stress and porosity. The density of the soil is indicated by its porosity. All right, with that basic review, let's dive in. We're going to look at two primary tests for measuring shear strength of soils. The first and most simplest, or the simplest of which, is the direct shear test. And with the direct shear test, you have this, it looks kind of like a box, and you fill it with soil. And there's a porous plate on the top and the bottom that allows water to move through it. And then the upper box can slide relative to the lower box. So when you first put this together, these are lined up, and you fill it completely with soil. And then you have this plate on top that fits right here, and that puts a normal load on the top. And that, divided by the area this area right here would be the total stress that's applied. And then the top box is moved laterally in this direction, the upper box, and that causes a shearing plane to occur. And you measure the shear resistance, how much force it takes to to push to move that laterally. And you do this and you repeat it for a number of different normal loads, total stresses. And what happens, so if you do one test and you give it basically this much normal stress, you may measure this much shear resistance, and then you do it again at a higher stress. The higher the stress you put on it, the normal stress, the more shear resistance you're going to have, because it squeezes those particles together, increases that effective stress. And you do that a number of times and plot it. And in general, this forms a line. Sometimes it can be curved, but usually it's reasonably close to a line. And this is called the shear strength envelope, or the Mohr Coulomb envelope. And then once we have this line, we can estimate if we know that where this line intercepts the axis here is called the cohesion intercept. The angle of this line is called the friction angle. And so if we say C, the shear strength is equal to C plus sigma tan phi, that is basically the equation of this line. The tangent of this angle is the slope of the line. So this is just the equation of a line. All right, so this should look, again, this is supposed to be a review, so hopefully you've all seen this before. And another really important thing to consider when we do these tests is whether we have drained or undrained conditions. With drained conditions, water is able to freely flow out, and the pore pressures are allowed to dissipate. And so why would there be pore pressures? When you apply this normal load, that causes the pore pressure to increase. And sometimes when you shear the soil, that shearing process causes pore pressures to change along that interface where it's shearing. We'll talk more about that as we go. All right, so if you're simulating drain conditions, there's free drainage. The forces are applied very slowly, given the pore pressure time to dissipate. Under undrained conditions, there's very little flow of water that is allowed, and the application of the stress is fairly rapid. It doesn't give adequate time for the pore pressures to dissipate, either due to loading or shearing. Why would it take time for pore pressures to dissipate? This is the time required for 99% drainage is, there's an empirical relationship. It's a function of the maximum drainage distance squared. So if you double the drainage distance, and that's maybe the farthest distance from the middle of the soil to where it's draining to, if you double that, the time required would go up by a factor of 4. And it's also a function of the coefficient of consolidation. And figure 3.8 on page 28 of your textbook has a diagram showing different CV values for different soils. You can get that CV value from a consolidation test. And it's a function of the hydraulic conductivity and permeability of the soil. Basically, sands, gravels have a very high coefficient, or they drain very rapidly, and so the time required goes down, so they have a high coefficient of consolidation. And clays have a very low coefficient of consolidation, so that would cause that time to go up. And the simpler way to think of it is that the hydraulic conductivity, the permeability of the clay is low, therefore it takes more work for those pore pressures to drain. So why is this important? Because those changing pore pressures impact our effective stress. Remember, the effective stress is the total stress minus the pore pressure. So when the pore pressures change, the effective stress changes. Why would the pore pressures change? Well, the normal load, the weight you apply to the soil, whether that's applied or removed, that causes the loading conditions will change that pore pressure. So when you first apply a load to soil, that load is the increase in the load all goes to the pore pressure, which then the soil will try to drain. But if it takes a while to drain, and it'll take a while for that load to be transferred, and eventually that the pore pressures dissipate, and then that excess load will then be carried by an increase in effective stress. Anyway, a rising falling water table, dissipation of pore pressures due to drainage, dilation and compression due to shear stress. This is the other thing I mentioned. As you shear a soil, it can dilate or compress, which can cause the pore pressures to change. So, this is I just mentioned something that we'll revisit here. If you increase the normal stress on a soil, so basically you apply a load, you're changing the normal, so you're adding a load, say, on top of the soil. So the new total stress would be the initial the stress before you applied the load plus the change in load. And the pore pressure would be the initial pore pressure plus the change in load. So initially when you apply a load to saturated soil, that increase in the load is felt all the way through the pore pressure in the soil. It's carried by the pore pressure initially. Now remember, the effective stress is equal to the total stress minus the pore pressure. So this is the total stress after you've applied the load, which goes right here. This is the pore pressure, which goes right here. And so the delta sigmas cancel, and you get the effective stress right after you apply the load is the initial total stress minus the initial pore pressure, which is just another fancy way of showing that initial load is carried completely by the pore pressure, and initially, and if drainage has not occurred yet, those pore pressures will not dissipate, and that the effective stress will remain unchanged. But again, as drainage occurs, that load will eventually be transferred. Oh, not the load, I mean the delta signal will be transferred from the pore pressures to the effective stress. Okay, so since shear strength is a function of effective stress, it's very common to plot on this failure envelope, instead of doing total stresses, we do effective stresses, and then whatever line you come up with, the cohesion intercept is C prime, and the friction angle is phi prime. That's the effective friction angle and the effective cohesion intercept. And that gives us this equation here. The shear strength is equal to C prime plus sigma prime tan phi prime, where sigma prime is equal to sigma minus u. Now, sometimes you will see, so this line here, sometimes it goes right through the axis and there is no cohesion intercept, and that occurs when you have normally consolidated clays. And normally consolidated clay means the stress that the clay is currently experiencing is the highest it's ever experienced. Whereas an over-consolidated clay, designated, or soil I should say, by the OC, it's been subjected to strong, large stresses in the past, and that makes it stiffer and stronger, and it behaves a little differently. It has a cohesion intercept, meaning even if you have no stress applied on it, it still has some cohesion and implicit strength, whereas a normally consolidated soil, it would not. And so oftentimes we're just looking at this part of the graph. Theoretically, once you reach a stress that's the maximum the soil has ever experienced, since it was deposited, then these lines would converge. But if you see a shear strength envelope with no cohesion intersect, it means you're dealing with a loose sand or a normally consolidated clay. If you see a cohesion intercept, it means you're dealing with a stiff sand or an over-consolidated clay. All right, another thing that is really interesting to look at is called a stress path, and that is how these stresses change once you start applying a load. So let's suppose, for the sake of argument, that you're doing a direct shear test, and when you first begin the test, the effective stress is right here where it says initial stress, and then you begin to apply shear by sliding those plates across one another. What happens? Well, if you have drained conditions, as you apply that shear, the effective stress does not change, and the shear stress gradually increases until it reaches this failure envelope, and then it fails. But if you have undrained conditions, it can take a couple of different paths. If for normally consolidated clays or lightly over consolidated clays, or for loose sands, and what I'm talking about here is the majority of soils we deal with. What happens is as you apply shear stress, those particles in the shearing zone, they go from a loose state to a more dense state, and that increases the pore pressure in the shearing zone. That increase of pore pressure causes the effective stress to decrease, and so it follows this path. The more you shear it, the lower the effective stress gets, and eventually you fail. And it could be anywhere along here. I just drew a sample path. Now, there are some soils, which would be a really dense sand or a heavily over-consolidated clay, where when you shear it in the shearing zone, it goes from a dense state to a more loose state. And in that case, that causes the soil in that zone to dilate, which creates a negative pore pressure. That negative pore pressure would actually cause the effective stress to increase. So there are some soils that when you shear them under undrained conditions, they actually get stronger. And it follows this path here. So the drainage conditions are really important to understand when we're analyzing these soils.